So far we've looked at a number of applications for vectors, velocity vectors, we've looked at displacement vectors, and today we're going to look at force vectors. And here's one example. You and a friend push a box with forces of 10 pounds and 20 pounds respectively. Now realize that there are many different ways that this object could move based on you and your friend pushing this object. If this were the object that I had, if both of you push on this side versus if one of you pushes on this side and one pushes on this side, or this person could move over on any type of angle to push this way, or possibly just try to oppose the person, maybe push it on this side. So if we have these two forces acting on this box, we have no idea how this object will move. So we're going to look at, first of all, we're going to show the minimum possible total force on the box if these two forces are applied. Remember, in physical science and possibly in physics, you worked with free body diagrams, and we'll review some simple ones and not go into a lot of detail on these, but we'll look at a free body diagram. So here's my object, my little box, and if we wanted to have the minimum possible force, then we would need to have the people pushing on the objects on this box in opposite directions. So on our free body diagram, we would have one person pushing from this side. Say this person is pushing from this side and applying 20 pounds of force. And then the other person would have to be pushing on the opposite side and would have 10 pounds of force. And so we know, we can see what would end up happening as far as the box would move. However, the box would move in such a way that it would be shifted in the direction of the person who has more force. Now, if we want to apply this idea to a situation of having it work with vectors, here's one of my vectors pushing to the east. I could have had this go north, south, any direction, but I wanted them to be in opposing directions. So I just chose to have this one push to the east. And if I want to add this vector and the opposing vector together, that would cause me to have the minimum amount of possible force on that box. So we know that when we add vectors, we always add vectors head to tail. So we plop one down. I'll put the first one in standard position, and I could truthfully start with the 10 first or start with the 20 first. The sum of the two vectors will end up being commutative, that you'll end up getting the same answer regardless of which one you put first. But let's say I start with the 20-pound force. And so here's my 10, 20-pound force being applied in this direction. And then we have the other vector. I need to have its tail, kind of move this vector down, need to have its tail plopped right here on top. Now I'm going to do it in a little bit different color so that will accentuate the difference between the two. And so there's the head of the one attached to the tail of the other. Now we know that the resultant vector is what our sum is, and that would be our resultant vector. So we know that if we are adding these two vectors, the 20-pound, which is going to the east, and the 10-pound vector, which is pushing from the west, that the resultant vector is this green vector that I've drawn, and in rectangular form, or component form, that vector would be 10 pounds of force and 0 pounds of force in the northerly direction. Now, on the other hand, if we wrote it in, say, polar form, we know the magnitude of the resultant vector, which I have in green, would be 10 pounds. And the direction, if I have it in polar form, would be 0 degrees. Now, if we did it in terms of a common form vector, or we wanted to be compass bearing, we would have said that was at 90 degrees. Now let's look at another example. Change the angle at which these two people are pushing. So you push the box with a 10-pound force while your friend pushes with a 20-pound force, except this time the angle between you and your friend is 50 degrees. Now once again, I don't know which direction truthfully you're pushing. I just know that your friend is pushing 50 degrees to that. So I have actually quite a few ways I can draw the free body diagram. And if I don't give you information as far as where the direction of the first push, that would be up to you. So there are a few different diagrams that could be drawn from this. However, let's say that once again my friend is pushing off to the east like that with a 20-pound force. Now I know that the angle between us would need to be 50 degrees. So the angle at which I would push would need to be 50 degrees. Now I could draw it downward or I can go upward, and that would be my choice. Let's say I go upward. There has to be a 50-degree angle between these vectors, and I need this vector that I'm pushing to be 10 pounds of pressure. So there's our free body diagram. Now we know that's not how you add vectors. Vectors have to be added head to tail, but that's how my free body diagram would look. So I'd be pushing this way, or my friend would be pushing this way, and I'd be pushing this way, and we would have a 50-degree angle. Now if we want to add those vectors, remember we can add either my friend's vector plus my vector to get the resultant, or my vector plus my friend's to get the resultant. Either way would be fine. So we'll get a little axis system here. Now, I'm going to start with doing the same thing that I did up above, and I'm going to have my friend's vector excuse me, be the first one that I draw. So let's say this is 10 and this is 20 pounds of force, and here is my friend's vector. And now when I add my vector onto it, I have to go head to tail. So I need to draw my 10-pound vector here. So I know that this is 10 pounds long, and I know that this is 20 pounds of pressure. I know that angle is 50 degrees. Therefore, I know this angle is 130 degrees. And this is the vector I want to find. That's my resultant vector. And so if I call that length of that vector z, I know that is my resultant force. It's how the object is actually going to have how much force and in what direction it's going to travel. So I know I need to determine what the length of this vector is, and I'm going to need to determine what this little angle is. I'll just label it theta. So we have a side angle side. Law of cosines is our natural formula to use here. And so we have side squared plus side squared minus 2 times the product of the sides times the cosine of the included angle. And you double check the degree mode on your calculator. I did that, came up with a calculation of 27.52 pounds. Store that value so you use more decimals than what would be listed here. And then once I know this angle, and I know this side now, I can use law of cosines to determine what this angle is. I can use law of sines. Now I know this is an acute angle, so I know I'm not going to get fooled by law of sines here. So I'll just set it up with law of sines. So sine of the angle is to 10 pounds. Its side opposite, as the sine of the angle of 130 degrees, is to its side opposite, which is that stored value, the 27.52 pounds. And multiplying by 10 pounds and taking the inverse sine, I find that that angle is 16.2 degrees. So now I'm ready to write the resultant vector. I can put that into a polar form. That magnitude of the vector is 27.52 pounds. The angle in standard position would be 16.2 degrees. I could also write it as a component form vector. I did the calculation. Now I would have to figure out what its x component is and its y component, and and I can use that little right triangle that's formed right here to do that, knowing that this is the hypotenuse. Use my sine function to find the y coordinate, y over the hypotenuse, and then find the x component with the cosine function, and I found those to be 26.43 pounds and 7.66 pounds. And naturally it makes sense that this direction is much longer than this. I can see that from my relatively well-scaled diagram. And now it's time for you to practice.